Hi students, today we're going to do 11.4 nonlinear inequalities in one variable. So nonlinear means that we could have quadratics, we could have some, equations that wouldn't just be graphed as a straight line. Inequalities means that we are not going to say two things are equal. Instead, we're going to use these expressions greater than, less than or equal to, greater than or equal to. So those are the different relations that we're going to have. And because of that, our solutions are going to be any value that makes that inequality true. And this happens to usually be a range of values. So our solutions are going to be written in interval notation. So the starting on the number line to the ending on the number line, right? So right here, I've got an example for us. X squared minus 7x plus 10 is less than or equal to 0. So this is a quadratic because it's a squared, but it is an inequality. So the solution to this are any values of x, any number that we could plug in for x that makes it so that that number squared minus that number times 7 plus 10, any number that makes this expression here less than or equal to 0 is a number that makes this true. So it's a value that x could take on, and that's considered a solution. All right. So we have some steps to solve these nonlinear inequalities. And it's pretty straightforward process. So because our solution is going to be a range of values, what we really want to do is figure out the endpoints of that range. Okay, so the endpoints of this range of values that make this inequality true are going to be on the border of the values of x that make this equal to 0, right? Because if the value of x changes one way or the other, it's going to pop us to the left or to the right side of 0 on the number line. And so the values of x that make this equation strictly equal to 0 are going to be the values of x that are on the endpoints of the range of values that make this equation true. Okay. So for that reason, the first step that we're going to do is solve what we call the related equation. So this is an inequality. We're going to rewrite it as an equality, as an equation, and we're going to solve that. So we're going to figure out the values of x that make this exactly equal. And those are going to be the endpoints to our range of values that make this inequality true. So once we find the solutions to this related equation, then we can use those solutions to separate our number line into some different regions. And we just have to test one point that is strictly inside of each region in the original equality to see if indeed it makes this stuff less than or equal to 0. If it does, then everything in that region is a solution. If it doesn't, then nothing in that region is a solution. Okay. The very last thing you want to be careful of when you are writing your solution in interval notation, keep in mind that if we have the less than or equal to signs, that means our endpoints will be included and we're going to use brackets. If we have strictly less than or strictly greater than, then we are going to use parentheses to indicate that we are not including those endpoints. Okay, so let's go through this example. Step 1, solve the related equation, which is here in blue. Since it's a quadratic, we are going to factor that so we can get that x is either 2 or x could be 5. Both of those things make this equation equal to 0. Those are going to let us separate the number line into some regions. So we see we've got our number line here, we've got x at 2, x at 5. And so those 2 points actually give us 3 regions on the number line. The regions could be from -infinity up to 2, from 2 to 5, or from 5 to infinity. And notice that because I have a less than or equal to sign, I'm actually writing these with brackets because if we test a point in that region and it satisfies this inequality, then we are going to write that interval with those brackets because we are including the points 2 and 5. Okay. In fact, we already know that x equaling 2 is a solution to our inequality, and that x equaling 5 is also a solution because we know that when x is 2, this thing equals 0, and that satisfies being less than or equal to 0. Okay. So just notice why I use parentheses where I did and why I use brackets where I did. Okay. Then we want to test a point inside each region. Make sure you are strictly in the region. Don't use x is 5 or x is 2, okay? Because those are on the end point of a region. We already know those are going to make it 0, so it's not going to tell us anything about the region inside. So you can pick any point in each of these 3 regions. I like to pick something easy. So in my first region between negative infinity to 2, I'm going to throw in 0. Between 2 and 5, I'm going to pick 3, but you could also pick 4 or any decimal value between 2 and 5. And from 5 to infinity, I'm going to pick 6. Okay, you could pick 10 if you wanted to. So you plug in a point into our original inequality. So let's say that x is 0. When x is 0, we get that the left-hand side equals 10, and it will say 10 is less than or equal to 0. That is not true. So the result is false. There is x being 0 is not a solution to the original inequality. Okay, and knowing that, we can throw out that whole region that contains 0. Then we'll plug in the value 3. When you plug in x is 3, you will get that the left-hand side is less than or equal to 0, making this inequality true. And that tells us that that whole region is contains solutions to our inequality. When we plug in 6, we end up that the left-hand side is not less than or equal to 0, so that region gets thrown out. So our solution here is the region from 2 to 5, including the endpoints 2 and 5. Any number between 2 and 5 and including 2 and 5 satisfies this inequality. So that is our solution there. All right. Let's try to make sense of this visually. If we wrote this as a function, so if we drew the related function for this equation, it would look like this: y equals x squared minus 7x plus 10. And you'll find that this function is less than 0, right? The y values, the outputs take on values less than 0 between the numbers 2 and 5. So that's why the solution is x values between 2 and 5, because x values between 2 and 5 satisfy this less than or equal to 0 for the output. Okay. And that just kind of repeats what we saw on the other side. So we've got our region between 2 and 5, and we are including 2 and 5 because we have a less than or equal sign. That's with polynomials. Now let's check it out with rational inequalities. So the difference between rational inequalities and polynomial inequalities is that with rational inequalities, we also have to consider the possibility that our values here, the value of this expression could switch from something less than 1 to something greater than 1 without actually passing through being equal to 1. And that can only happen when we have a discontinuity, and that discontinuity is going to happen when the denominator is equal to 0. So when we solve nonlinear inequalities for rational expressions, rational inequalities, we have to also add in to the possible endpoints of our solution regions, anything that makes this undefined. And so that is going to be when x equals 3, this equation is undefined. And so that could be an endpoint to a solution region. Then we'll go through the same steps. We're going to solve the related equality. And when we go to solve the related equality, in this case, we actually get that there are no other solutions. There's no value of x that's going to make the x plus 2 the same as x plus 3. So nothing is going to make this fraction equal to 1. So we don't have any solutions to the related equation, but we do know that one possible place we could switch from being less than 1 to being greater than 1 is at that discontinuity. So the only point we have to break up our regions is this x equals 3, which gives us the two regions, x from negative infinity to 3 or x from 3 to infinity. Notice again, I am using the parentheses, not the brackets here, to define these regions because we have a strictly less than 1. But also, actually in this case, it's not because we have the strictly less than 1. The reason I'm using the parentheses here is because our function or our equation is undefined when x is 3. So x being 3 cannot be a solution to this because it is undefined at x equals 3. So we can never include the point 3, x equaling 3 in our solutions, okay? Because it's undefined at 3. So we've got our two test, our regions. We need to test a point in each of them. I'm going to test 0 and I'm going to test 5 because those just seem like easy numbers. You could use a 4 here. You could do a 2 up here. So when we plug in 0, we get 2 over negative 3, which is indeed less than 1. So that region, that point in that region makes this inequality true. When we plug in 5, we get 7 over 2, which is bigger than 1, and that makes this inequality false. So we know that the region negative infinity to 3 is contains all the solutions to this original inequality. So our solution is negative infinity to 3 with parentheses. And just to note again, the 3 has parentheses on it, not because it's a strict inequality, but actually because the 3 is not in the domain of our function. Okay, so even if we had a strict inequality, even if we had a less than or equal to in this situation, we would still have the parentheses because 3 is a point that is undefined. If we had another point that, say, solved this related equation, then we would have to ask ourselves about whether our inequality is a strict inequality or an or equal to inequality. All right. Let's just take a quick look at the graph, the related graph to this guy. And as you can see in this related function, at x is 3, our function's undefined. There's a vertical asymptote where x is 3. And you see that because where x is 3, our function is allowed to jump from being less than 1 to being greater than 1 without actually ever taking on the value of 1. It jumps from one side to the other at that discontinuity. And so that's why that discontinuity has to be included as one of the endpoints for our region. Okay. Whew. All right, that is 11.4 nonlinear inequalities in one variable. Make sure you understand how rational inequalities need the points that are discontinuous to be included. If it's discontinuous at that point, you are always going to use a parenthesis. Now, if the point actually solves the related equation, then you have to look at your inequality sign to determine whether you need a parenthesis or a bracket. All right, good luck.